Okay, we're gonna finish up our chapter on solutions. We don't have much left. So this slide is a slide that hopefully you saw a similar chart or graph I should say, in Chem 107. It's a phase diagram. So this is the phase diagram. It should be for water, but it's just saying for any solvent, which would be true. It doesn't matter what the solvent is. So I said that the colligative properties are related to each other. And so vapor pressure lowering of a solution is really why the boiling point of a solution goes up and the freezing point goes down for solutions. So this is showing us the pink lines would be the equilibrium line between a liquid and a vapor. And this one over here on the left would be the equilibrium line between a liquid and a solid. So that's essentially the points at which something melts for the solid to liquid and where something boils for the liquid to vapor, because the point at which liquid and vapor are in equilibrium is its vapor pressure, and the point at which something boils is when the vapor pressure equals atmospheric pressure. So if we look at something like 1 atmosphere on here, so the pressure of 1 atmosphere and how the temperature changes at which you cross those lines. So let's start out with the boiling point elevation. So if the vapor pressure is lower above a solution, then the green line is below the pink line for a solution, and the pink line is the pressure of a solvent. And so at 1 atmosphere, the point at which you cross the line is going to be at a higher temperature. So the change in boiling point is always going to be bigger if you have a solution versus a solvent. So this is simply based on the fact that the vapor pressure goes down. And then when you think about why the temperature at which something freezes is lower, so if the vapor pressure line is lower, it's going to cross lower, and that's the point at which the solid line goes up. So then the solid line goes up, and so the green one is for the solid that's part of a solution, and the pink one would be if it was pure. And so it's going to freeze always at a lower temperature because that line is always going to start out to go up a little bit left of a pure liquid's solid liquid equilibrium line. So this just gives you a couple of equations. So for non-electrolytes, change in boiling point is equal to K times molality. Change in temperature of freezing is Kf. So Kb and a Kf are just constants for a particular system. One is for the boiling point elevation, one is for the freezing point depression, but we're going to use units of molality here. And then on the right, if you have an electrolyte, you have to take into account, let's go back to our Van Hoff equation. Maybe wasting your time, but I thought it would be good to look at that Van Hoff equation. There we go, sorry. So remember, if it's an electrolyte, that means when it dissolves in water, you form ions. And so we know for something like a weak acid, that's not going to be 100%. So if your I wouldn't be 2, but it might be something above 1, something less than 2. So when you look at freezing point depression and boiling point elevation, right here, then you have to add that Van Hoff equation. So how many particles do you get? So M would be molality of the substance you put in. I would be essentially telling you how much of it dissociated. So this is just a small table of the Kf and the Kb, and those are for the solvent. So for the thing freezing or vaporizing. And this shows you they were related to the vapor pressure lowering, but they're also, you can think of them in the same way that we thought about why vapor pressure is lower. So if, let's see, this is for the boiling point going up. So if you have a pure solution, remember, or if you have a pure solvent, it has less entropy than a solution. And so the blue line is bigger, the delta S is bigger for the solvent going into the vapor phase if it's a pure solvent. But if you have a solution, then the solution already has more entropy than the pure solvent. And so you're starting out a little bit higher. So you don't gain as much entropy going into the vapor phase. And so that means when you solve for temperature of boiling, if we assume the delta H of vaporization is a constant, so on the right-hand side, and that the delta S of vaporization is lower for the solution, then the temperature at which that solution boils compared to the solvent is always going to be larger. And then you can do the same thing for the freezing point depression. So now going from solid to to a liquid. So if you're melting the solid and making it into a into the pure solvent, that entropy you gain isn't going to be as much as if you have a solid and you're making it into the solution. So you're going to melt it and it's going to be part of a solution. So that has a higher entropy. So the delta S of fusion for the solution is going to be bigger. And we're assuming that the delta H of fusion is the same, so the numerator is the same, but the delta S of fusion, if you're making the solid into a solution, is going to be greater, and therefore the temperature at which that happens is going to be smaller. So this is just asking you to do a calculation. So what's the freezing point of a solution prepared by dissolving some magnesium chloride in water? And it gives us the Van Hoff equation. So Van Hoff factor of 2.7 says that magnesium chloride doesn't completely dissociate. If it did, it would be 3 because you'd get 1 magnesium 2 plus and 2 chloride ions, but it's slightly less than that. So it's not completely dissolving. So we're going to calculate the moles of magnesium chloride we put in, and then we're going to calculate the molality of the solution. So we have the moles of magnesium chloride. 110 grams of water has to be converted to kilograms. And then you'll have 0.71 moles of magnesium chloride you dissolved in a kilogram of water. But we have to take into account how many particles we have. So we have to calculate, or we have to now use the I factor. So we have to take the KF for water out of the table, 1.86 in the units we're working in, the molality of the magnesium chloride we made, 0.71, and the Van Hoff factor, 2.7, which is unitless, to find out that we get a change in temperature of freezing of 3.6. And then you just have to know that it's always freezing point depression, so that it's always subtracting that from the original temperature at which it would have frozen. So water freezes at 0. So it's 0 minus 3.6 is the new temperature. So if you want the temperature, you have to think about whether or not it's depression or elevation. So the last colligative property is osmosis. So osmosis is the passage, and it's also, so it's a colligative property, depends on the number of particles. So it's the passage of solvent through a semi-permeable membrane from the less concentrated side to the more concentrated side. So osmotic pressure is the amount of pressure that you'd have to exert in order to stop osmosis from happening. And this is just showing you a picture. Makes sense that pure water would like to go over to the side where there's more entropy. And so water has a natural tendency, if it's in the pure state, sitting next to a solution, to dilute that solution, and that increases its entropy. And so essentially you're trying to reverse that by applying a pressure and stopping that from happening. So calculate the osmotic pressure of 1 molar glucose in water at 300 K. So the equation we use is molarity times the gas constant times temperature times the Van Hoff equation. So we have a mole oh, it's 1 molar, so we know it's a mole in a liter. We have the gas constant, liter atmospheres, K mole, times Kelvin as our temperature. So we get 24.6 atmospheres. Glucose, we learned earlier, doesn't dissolve to make cations and anions, so the I factor is 1. So osmotic pressure is 24.6 atmospheres. So you'd have to apply 24.6 atmospheres to that piston in order to keep it from going in and diluting your glucose solution. Okay, fractional distillation. So I actually think we might skip this part. You'll do this in organic chemistry. So it's really looking at the fact that your gas is always going to be more enriched in the more volatile component. So let's see if there's, yeah, so if something vaporizes at a lower temperature, that means it has a higher vapor pressure. And you can separate things like ethanol from water by heating them up and collecting the vapor. So you're always going to be enriched in the one, let's go way back here. If we go way back to our Rialt's law. Rialt's law. Yeah, if you go back here, whichever component has the greater vapor pressure when it's pure. Yeah, this equation makes more sense. So the total pressure up above a solution that has 2 volatile components. So if you have ethanol and water, for example, it's always going to be more enriched in the one that has the largest vapor pressure when it's pure. So because that's what's being multiplied by the mole fraction, that's going to always be the component that has the greater pressure in the vapor phase, and therefore you're enriching it, and you can therefore separate it by fractional distillation. As it vaporizes, gets more and more enriched in the more volatile component. If you keep collecting that and re-vaporizing it, you can get things to be almost pure. If you're trying to collect, so for example, if you make if you ferment something and have ethanol and water and you want to make it into pure ethanol, like make some form of gin or something that has a higher concentration than when you first fermented it, you can get it to the point where it's almost pure ethanol that you have in this process, but you can only get it to where it's 95%. So that's a whole another concept that you'll learn about if you take physical chemistry. So it's a good way to separate. Distillation is a good way to separate components that have different volatilities, but you can't always completely separate them. And that is it for the rest of the chapter on solutions. So we will stop there. We have one more chapter on electrochem, which